Related rates, Part 1. I suggest that you take a picture of the screen or pause the video and copy it down. This is a process that I teach my students to solve related rates problems. Pretty much anything that I give you, if you follow these steps in order with a little bit extra that I'll talk about, you can solve pretty much any related rates problem. It's also a slightly modified version of my general problem-solving process. But let's take a look here. First thing I have my students do when we're solving related rates or any other problem whenever possible is we draw a picture and we label it appropriately. If the measure, an area, length, etc., is changing anywhere in the context of the problem, we're going to call that a variable. Otherwise, label it as a constant. You'll see some of these things go on in the next few videos. Number 2, using the variables you choose, change each piece of given information into a calculus expression or equation. Number 3, find an equation that relates the variables. 4, take the derivative of both sides of the equation with respect to time t and chain out all variables. Number 5, plug in what you know, solve for what you don't know. The only thing you shouldn't know is what you're solving for. What happens sometimes is that there's more than one thing that we don't know. That just means we missed something earlier when we were labeling or drawing or changing information, or perhaps it was just implied and we missed it. So this first example, I'm going to start kind of in the middle and then work both backwards and forwards so we can see a little bit better the problem-solving approach. So this is kind of like if I arrived at steps 2 and 3, right, have an equation that relates variables. I'm writing things down in simple calculus expressions or equations. Now, where do you think this came from? Well, first of all, what kind of shape do you think we're dealing with? If you said circle, you would be correct. How do we know it's a circle? Because I said A, or area, is pi r squared. We know that's the area of a circle. And of course, a circle has a radius. Now, should we label this, if we were labeling, r, or should we label a number? Well, it says r equals 2. So you might think, well, we'll just plug 2 there instead of r. But it also says that dr dt equals 3. Which means my radius is changing in the context of the problem. So if I were to label this appropriately, I should call it r. Now, what do you think the words might say if it was a word problem and it gave me this, instead of saying dr dt equals 3? Well, it's very common to say something like, the radius is changing at a rate of 3. Now, usually we have units. I didn't give units here. And my units are usually in, if it was radius, it might be inches per second or meters per hour or whatever it might be. But it'd be some, in this case, length per time. Now, is the circle getting bigger or is it getting smaller as time increases? Well, since dr dt is positive, that means r is increasing, which means the circle is increasing. as well. Now, what are we trying to find? I know mathematically we're finding dA dt, but in words it would probably say something like this. Find how fast the area of the circle is changing. Now, at what point? Well, in this case, I didn't give you a time. I gave you a radius. So this is probably what would have been given in a word problem, because related rates are generally speaking in word problem form. And I would have known to draw my picture and label and write all these things down. Find this, given this, get an equation that relates the variables, which is what I have. So now the next step of the process says, let's take the derivative of my equation, both sides, with respect to time. So kind of start in the middle, went backwards, now I'm back in the middle and going forwards again. If I take the derivative of this, chain out every variable, I get really 1, but times dA dt, the chain out, equals 2 pi r, variables don't match, so times dr dt. And the last step, hopefully, is plug in what you know and solve for what you don't know. Well, we're trying to find dA dt. That's the only thing we shouldn't know. And we can plug in r, which we do know, which is 2. And dr dt, which we also know, which is 3. And we get dA dt is 12 pi units squared per time. Let's take a look at one example, start to finish. Again, you might want to take a picture or pause the video to copy the problem down, which will be the same in the next, hopefully, 2 videos I do on related rates, just with more somewhat typical examples. All right, suppose that I have 2 cars that start from a common point A and they leave at the same time. One travels east at 80 miles per hour, the other travels north, due north on a straight line, as if that was possible, at 45 miles per hour. How fast is the distance between them changing at t equals 3 hours? All right, so let's draw a picture. That's the first thing I like to do in related rates problems. I like to draw a picture. So a car is starting at point A, 2 cars. One's, call this point A over here. One's traveling east at 80 miles per hour. So I have a length over here that's changing, which means I need to label it a variable. The other car travels north, so this length is also changing. Let me put arrows as well, indicate direction of motion. So that length is changing, so I'm calling it a variable. And I want to find how fast the distance between them is changing. So I probably need a third side. Let's get a third side over here. And I want to find how fast this distance is changing. Well, it's changing, so we're going to call it a variable, of course. All right, so we have the picture. We have it labeled. Now, let's pick the information out one piece at a time and change it into a simple calculus expression or equation. Let's look at the 80 miles per hour. Well, that's this over here. So I know that x is changing, dx dt is changing, x is changing, at a rate of 80 miles per hour. So dx dt equals 80. The y is changing as well at a rate of 45 miles per hour. And the problem says So I've taken one piece of information, another piece of information. Find what? How fast the distance, how fast r is changing. Find dr dt at t equals 3. Okay, it looks like I've used all the information that's been given. Now the next step I do is I want to find an equation that relates the variables. Hopefully you already realize we're going to be doing Pythagorean theorem. So we can do x squared plus y squared equals r squared. And we want to take the derivative of this with respect to time. And we're going to chain out all of our variables. So we get 2x times dx dt plus 2y times dy dt equals 2r times dr dt. I will get rid of the 2's just to make it a little simpler. Now let's plug in what we know and solve for what we don't know. So plug in for x, and we immediately hit a problem, which I like to do right away when we're doing problems. I don't know what x is. I don't know what y is. I don't know what r is. I should know all of those because the only thing I should not know is dr dt. Does that mean we did it wrong? Perhaps, but usually not. It usually means we missed something that was implied. And in fact, we never really used this piece of information at t equals 3, did we? So how can I use that piece of information? If both cars start at point A and x is going 80 miles per hour for 3 hours, then I know that x equals 240 miles. That is, it equals 240 miles when t equals 3. Likewise, at t equals 3, since y is going 45 miles per hour, at t equals 3, y equals 135 miles. Well, how about r? Well, r is Pythagorean theorem. So r is going to be the square root of x squared plus y squared. And now we have all the information that we need to plug into our equation. This is miles. I'll finish off my units. Now I can plug in. I have x is 240. dx dt is 80. Y is 135. dy dt is 45. R is this square root, so instead of writing it over and over again, I'll just move it over by dividing and put R down below as 240 squared plus 135 squared. And notice that the only thing that we have left over, I'm going to give myself a little space here. The only thing that we have left over on the right side is exactly what we were looking for, dr dt. Now, I'm not going to simplify this one. You can plug it in the calculator and get an answer. And I left a little space right here because if I give you units to start, generally speaking, I would like them back. And the problem, R is a length, so miles, then time, of course, we use as hours. And that is how fast the distance between the two cars is changing at t equals 3.